expressing the angle in terms of sine. Welcome, everyone. Let's begin our new session on expressing the angle in terms of sine. Now, if you recall from our previous lesson, we focused on how to calculate the angle theta between two lines using the cosine formula. That method is very reliable, but it isn't always the most efficient tool for every job. As we move forward into more complex geometric problems, for instance, when you are trying to find the shortest distance between two skew lines, or when you need to calculate the area of a parallelogram formed by vectors, you will find that it is actually much more convenient and mathematically direct to express that angle using the sine function instead. So today, we are going to learn how to derive and apply that sine-based approach. Conceptual understanding. Now that we've established why we might want to switch from cosine to sine, let's look at the conceptual foundation behind this transition. The relationship between the sine and cosine of an angle is governed by the fundamental trigonometric identity, which you should all be very familiar with. Sine squared theta plus cosine squared theta equals 1. By simply rearranging this identity, we can isolate the sine component. If we subtract cosine squared theta from both sides and then take the square root, we can derive the sine of the angle as sine theta equals the square root of 1 minus cosine squared theta. Now, here is where the connection to our previous lesson comes in. In the last section, we learned how to express cosine theta using the direction ratios, specifically a 1, b, 1, c1 and a 2, b2, c2. If we substitute that entire cosine formula into this identity and perform the necessary algebraic simplification, we arrive at the specific expanded formula for sine theta that we are about to see on the next slide. The mathematical formula. Now that we understand the trigonometric identity that links sine and cosine, let's look at the actual formula we can use in practice. For two lines, let's call them L1 and L2, which have direction ratios of a 1, b1, c1 and a 2, b2, c2 respectively. The sine of the angle theta between them is given by this expression. In the numerator, we have the square root of the sum of three terms. The first term is the quantity a 1b2 minus a 2b1, all squared. The second term is the quantity b1c2 minus b2c1, all squared. And the third term is the quantity c1 a 2 minus c2, a 1, all squared. Now, for the denominator, we take the square root of a 1 squared plus b1 squared plus c1 squared, and multiply it by the square root of a 2 squared plus b2 squared plus c2 squared. It looks quite complex at first glance, but don't worry. In the next slide, I am going to break this down into a simple, step-by-step process so you can calculate it without any confusion. Step-by-step breakdown of the formula. Now that we have seen the complex-looking formula for the sine of the angle, you might be feeling a bit overwhelmed by all those variables. Don't worry, we aren't going to tackle it all at once. To calculate sine theta without making any errors, I want you to follow this systematic, four-step breakdown. Step 1. First, we need to identify our direction ratios. This is simply the process of extracting the components from your given lines. For line 1, we identify a sub 1, b sub 1, and c sub 1. For line 2, we identify a sub 2, b sub 2, and c sub 2. Having these clearly listed is crucial before you start any heavy lifting. Step 2, next we tackle the numerator, which contains the cross-product terms. This is the most calculation-intensive part. You'll need to compute the differences of the products of the ratios in pairs. First, calculate a sub 1 times b sub 2 minus a sub 2 times b sub 1, and then square that result. Second, do the same for the next pair. Calculate b sub 1 times c sub 2 minus b sub 2 times c sub 1, and square it. Third, calculate c sub 1 times a sub 2 minus c sub 2 times a sub 1, and square that as well. Finally, sum these three squared values together and take the square root of the total sum. Step 3. Now, let's move to the denominator, which represents the magnitudes. You need to find the magnitude of the first line's direction ratios by calculating the square root of a sub 1 squared plus b sub 1 squared plus c sub 1 squared. Then, do the exact same for the second line. the square root of a sub 2 squared plus b sub 2 squared plus c sub 2 squared. Once you have both individual magnitudes, multiply these two results together. Step 4. Finally, we reach the final division. Simply take the result you obtained from the numerator in step 2 and divide it by the result you got from the denominator in step 3. This will give you the value of sine theta. If you follow these steps carefully, as we are about to see in our next slide with the telecommunications tower example, the calculation becomes much more manageable. Illustrative example. Now that we have understood the formula and the steps required, let us apply them to a practical example. Imagine a real-world scenario. We have two support cables attached to the top of a telecommunications tower. The direction of the first cable is represented by the direction ratios 1, 2, and 2, while the second cable is represented by the direction ratios 2, -1, and 0. Our objective is to find the sine of the angle, theta, between these two cables. To solve this, we will follow the four-step process we just reviewed. Step 1. First, we identify our direction ratios clearly. For the first line, we have a 1 equals 1, b 1 equals 2, and c 1 equals 2. For the second line, we have a 2 equals 2, b 2 equals -1, and c 2 equals 0. Step 2. Now we calculate the numerator using the cross-product terms. We calculate the difference of the products in pairs. First, 1 times -1 minus 2 times 2. Second, 2 times 0 minus -1 times 2. And third, 2 times 2 minus 0, 1. This simplifies to -1 minus 4, which is -5, 0 plus 2, which is 2, and 4 minus 0, which is 4. We then square these values, giving us -5 squared, plus 2 squared, plus 4 squared. Summing these squares, we get 25 plus 4 plus 16, which results in the square root of 45. Step 3. Next, we calculate the denominator by finding the magnitudes of both lines. For the first line, the square root of 1 squared plus 2 squared plus 2 squared simplifies to the square of 9, which is exactly 3. For the second line, the square root of 2 squared plus -1 squared plus 0 squared simplifies to the square root of 5. Multiplying these two magnitudes together, our denominator becomes 3 times the square root of 5. Step 4. Finally, we perform the division. We have the square root of 45 divided by 3 times the square root of 5. We can simplify the numerator because the square root of 45 is equal to the square root of 9 times 5, which is 3 times the square root of 5. When we divide 3 times the square root of 5 by 3 times the square root of 5, the result is exactly 1. As a concluding note for this example, since the sine of theta equals 1, we know that the angle theta is 90 degrees. This tells us that the two cables are perpendicular to each other. As we will discuss in the next slide, being extremely careful with your signs during step 2 is vital to reaching this correct conclusion. Common mistakes to avoid. First, let's talk about index mismatch. This is a very frequent mistake. When you are calculating the numerator, you must remember to cross-multiply the ratios. A common error is accidentally multiplying ratios from the same line, such as a sub 1 times b sub 1. Instead, you must always pair a value from line 1 with a value from line 2, like a sub 1 times b sub 2. Always double-check that your indices are alternating. Second, keep a very close eye on your sign errors. This is particularly tricky during the subtraction phase in the numerator. For instance, when you are calculating b sub 1 c sub 2 minus b sub 2 c sub 1, if the second term, b sub 2 c sub 1, happens to be a negative number, that subtraction will actually turn into an addition. One small slip with a negative sign can change your entire result. Finally, don't forget the square root. I often see students successfully calculate the sum of the squares in the numerator, but then they move straight to the division without taking the final square root of that total. Remember, the entire numerator is enclosed under a radical sign. Now, before we wrap up our lesson and move on to the final summary, I want to pause and discuss some common pitfalls. Even if you understand the formula we just worked through in our example, it is very easy to make small computational errors that can lead to the wrong answer. Keep these 3 points in mind, and you will find much more success with these types of vector problems. Now, let's look at our final slide to summarize the key takeaways from today's session. Key takeaways. First, remember that the sine formula we've just explored isn't a brand new concept, but rather an alternative to the cosine formula we studied previously. It is directly derived from the fundamental trigonometric identity, where sine squared theta plus cosine squared theta equals 1. This means if you already know the cosine, you can always find the sine. Second, if you look closely at the structure of that complex formula in slide 3, you'll notice that the numerator, that entire square root part, actually represents the magnitude of the cross product of the two direction vectors. This is a very important connection to make if you are studying vector algebra. Third, the denominator is simply the product of the magnitudes of the direction ratios for both lines. It's essentially the magnitude of the first line multiplied by the magnitude of the second line. Finally, keep these two special cases in mind for your exams. If you calculate the sine of theta and find that it equals 0, it tells you that the lines are parallel. On the other hand, if sine theta equals 1, as we saw in our cable example in slide 5, it means the lines are perpendicular, or at a 90-degree angle to each other. To wrap up our lesson today, let's review the key takeaways to ensure you have a solid grasp of this concept. Keep these points in mind, and you'll be able to navigate these vector problems with much greater confidence.